write the empirical formula for the following compounds. Empirical is the whole number, the simplest whole number ratio. So S2Cl2 would just be SCl. All right, that's the simplest whole number ratio for A. B, C6H12O6, CH2O, right? Because we can divide them all by 6. C, NH3, that is the empirical formula. Can't get any simpler than NH3. H2O2, HO. All right? Oh, sorry, we skipped D. AS2O6, there's 1 AS for every 3 oxygen. So these are all the empirical formulas. A, B, C, D, E. All right? Good. Empirical formula, again, is just the simplest whole number ratio of atoms in the formula, the chemical formula. C70, 479, 481. A quantitative analysis of a sample of sodium pertechnate with a mass of 0.896 grams found 0.119 grams of sodium and 0.477 grams of technetium. All right, 0.896 grams of sodium per technate. So I'm guessing that was it TC? Yeah, TC. And the per technate ion, where's that? Yeah, TC. And O4, I'm guessing that that's the pertechnate ion. I'm not positive though, so it doesn't really matter though. And 0.477 grams of technetium. The remainder was oxygen. Calculate the empirical formula of sodium pertechnate. Radioactive sodium pertechnate is used as a brain scanning agent in medicine. So I guess we're not supposed to necessarily know what this is. We just know it has those components. And there's that much NaTCO, whatever it is initially. 0.111 grams of it is sodium, and 0.477 grams is technetium. So we can take 8.96 and minus these two, and the result will be how much is oxygen, right? So 0.896 minus 0.111 minus 0.477. So that's 0.308 grams oxygen, all right? So if we have this many grams sodium, this many grams technetium, and this many grams oxygen, and the question is, calculate the empirical formula of sodium pertechnate, all right? So the empirical formula, again, is the molar ratio, moles of hydrogen to oxygen, for example, right? H2O, there's 2 hydrogens for every oxygen, right? That's the molar ratio. And that's the empirical formula for water because it can't be reduced down anymore. H2O2, this is hydrogen peroxide. Its empirical formula is different. It can be reduced down to HO, right? So empirical formula is just the mole to mole ratio. So we have this many grams of sodium, but we want to know how many moles of sodium that is. All right, how many moles of sodium that is? Well, 0.111 gram, there's 23 grams for every 1 mole of sodium, so we can figure out that way. This one for technetium, how many moles of technetium are there? TC 98. So there's 98 grams of TC for every 1 mole of TC. And then for oxygen, there's 16 grams of oxygen for every 1 mole of oxygen. All right, so 0.308, we'll do the bottom one here first. 0.308 divided by 16. I'm getting 0.01925 moles of oxygen. For the technetium, 0.477 divided by 98, 0.004867 moles of technetium, 0.111 divided by 23.004826 moles of sodium. So that's how many moles of sodium, that's how many moles of technetium, and that's how many moles of oxygen. Now we just have to, we can write down that formula right there, for example. Again, it's not the simplest whole number ratio. I'm going to erase this side here. So if we knew it was Na 0.004826, Tc 0.004867, and then oxygen 0.01925. All right, so those are the molar ratios there, right? Well, that's kind of helpful, but not really, because we need the simplest whole number molar ratio. And we can get that by taking the smallest one, and it looks like this is the smallest one, and dividing them all by the smallest one. And what that does is that makes our sodium have number 1, and technetium 0.004867 divided by 0.004826. So that's 1.008. Oxygen 0.01925 divided by 0.004826. And that's oxygen 3.988. So now we can see that that's close to 1, that is 1, and that one's close to 4. So it looks like the formula is NaTCO4. All right? So, again, we were given how much mass, how many grams of sodium, technetium, and oxygen. We converted that to how many moles there were. We identified the top part here, we wrote down an equation with that many moles, that mole ratio, but we divided all of them by the smallest value to get a whole number ratio, and we ended up with the empirical formula for sodium per technetium. Good. 481. Now we're on to 483. A dry cleaning fluid composed of only carbon and chlorine was found to be composed of 14.5% carbon and 85.5% chlorine. All right, so that's it. What's the empirical formula of this compound? Well, here's some chemical. We don't know what the chemical is. All right, here's some chemical that's made of carbon, XCl-Y. We don't know CXCl-Y. We don't know how many carbons and chlorines are in the ratio of this specific chemical, but we know that 14.5% of the mass is carbon and 85.5% of the mass is chlorine. Therefore, we can, let's pretend like this is 100 grams in here. Let's pretend like this is 100 grams. Anytime we have percentages, it behooves us to pretend like it's 100 grams, because then we can say this is 14.5 grams for every 100 gram sample, and 85.5 grams, this is of carbon, and this is of chlorine, for every 100 gram sample. All right, so that's how many grams of carbon, that's how many grams of chlorine. We can do the same thing we just did on the previous problem, where we convert these to, there's 35 grams of chlorine for every 1 mole of chlorine. And we know how many moles of chlorine there are. 12 grams of carbon for every 1 mole of carbon, so we can tell how many moles of carbon there are. All right? 14.5 divided by 12. C7.25, that's how many moles of carbon there are. 85.5 divided by 35. 2.44 moles of chlorine, Cl 2.44. All right? So, whoops, I made a mistake there. I put 14.5 divided by 2. 14.5 divided by 12 is 1.21. All right, so this is our number of carbons and number of chlorines, but we have to divide them both by, we want it in a simple whole number ratio, so we have to divide them both by the smallest number. That'll give us 1 carbon for every 2.44 divided by that one, 2 chlorines. So 1 carbon to every 2 chlorines. All right, so that is the empirical formula of this compound. Let's double check on that one. 483. 483. CCl2. Good. All right. 485. Cinnamic acid, a compound related to flavor component of cinnamon, 72.96% carbon, 5.4% hydrogen. Hydrogen. 5.40. And the rest is oxygen. Well, we're not going to let them trick us. We're going to find out how much oxygen right away, right? 100% minus 72.96 minus 5.40. So we have 21.64% oxygen. 483 or 485. What's the empirical formula? So now we just need to find the empirical formula. Again, when they give us percentages like this, we can just assume that we have a 100-gram sample. So here's the chemical here. We have 100 grams of it, and this is how the percentages of the different components. So 72.96 grams of carbon, and we want to convert that to moles of carbon because, again, what we're looking for is the empirical formula, CHO, XYZ. This is the molar ratio, how many moles of this to how many moles of that to how many moles of that, right? So we want to determine how many moles, what the molar ratio is from the percent ratio, and we can do that by assuming a 100-gram sample, taking this as 72.96 grams, and converting that to moles of carbon, all right, and converting this one to moles of hydrogen and that one to moles of oxygen. So 72.96 divided by 12, there's 6.08 moles of carbon and 72.96 grams of carbon. 5.40 grams of hydrogen. 1 gram of hydrogen is 1 mole of hydrogen. Now, hydrogen kind of gets sticky sometimes, so we should use a couple of extra significant digits. 1.008 moles of hydrogen. And that'll give us how many, that'll tell us how many moles of hydrogen. So 5.40 times 1.008, that's 5.44 moles of hydrogen. So we have 5.44 moles of hydrogen. So now we see that the chemical formula so far, C 6.08, H 5.44. Okay, now we're going to find oxygen, 21.64. I'll erase this section down here so I can write it down, but I think you guys know what we're going to do. 21.64 grams of oxygen, and we want it in moles of oxygen. For every 16 grams of oxygen, there's 1 mole of oxygen, right? So 21.6 divided by 16, and that'll give us 1.352. 1.352 moles of oxygen. Divide them all by 1.352, right? Because that's the smallest, and we want the simplest whole number ratio. You don't have to divide. You can just kind of look at the numbers and try to finagle them, but it's easiest to divide to get yourself a starting point that's easier to finagle or adjust later on. So that means there's 1 oxygen, 5.44 divided by 1.352, that's H4.02, 6.08 divided by 1.3525, that's C4.495. So it looks like C4.5, H4O1. Still not whole number ratio. If we just multiply everything by 2, though, that'll give us C9, H8O2. 485, just double check that one really quick. C9, H8O2. good. 485. 487 now. When 6.84 grams of an organic compound containing only carbon, hydrogen, and oxygen was burned in oxygen, we got 1.312 grams of carbon dioxide, sorry. 1.312 grams of carbon dioxide. And we got 0.805 grams of H2O. 0.805 grams of H2O. Okay? That's how much carbon dioxide we got. That's how much oxygen we got. We were told that the compound was CHO, right? Just contained carbon, hydrogen, and oxygen. What's the empirical formula of the compound? So, if we burn it and we get carbon dioxide in a combustion reaction, CHOXYZ, combustion reaction, we're combining or oxidizing, try that again, plus O2, right? Some hydrocarbon plus oxygen. The products are always carbon dioxide plus water. All right? And we can see that from this chemical reaction, all the carbon that was in the beginning has to be on the carbon dioxide. And all the hydrogen from the beginning here has to be on the water. So we can relate the moles of water that we get to how many moles of water there were. And we can relate the moles of carbon dioxide that we got from the reaction to how many moles of carbon initially there were in the sample. We can't relate the moles of oxygen because we don't know how much oxygen came from here and how much came from here. But if we know that it just contained carbon, hydrogen, and oxygen, then we can use the difference later on to determine how much oxygen there was. All right, so if we have 1.312 grams of carbon dioxide, well, there's 44 grams of carbon dioxide, taking the molar mass, 1 carbon, 2 oxygen, 16, 16 plus 12. 44 grams of carbon dioxide for every 1 mole of carbon dioxide. So now we can know how many moles of carbon dioxide we got. For every 1 mole of carbon dioxide, that means there's 1 mole of carbon. So now, according to this, we can determine how many moles of carbon were in this initial compound. How many moles of carbon were in this initial compound? Okay, because for every 1 mole of carbon dioxide, we get 1 mole of carbon. We can do the same thing with water, right? 8.8059 grams of water. Well, there is 18 grams of water for every 1 mole of water. And for every 1 mole of water, there's 2 moles of hydrogen. So that'll tell us how many moles of hydrogen there were, right? Okay, so we'll do that really quick here. 1.312 divided by 44, right on this top one here, times 1 divided by 1, so there's 0.02982 moles of carbon, right? And here, 0.805 divided by 18 times 2, 0.08944 moles of what? Moles of hydrogen, right? Okay. Let's double check here. Did they? So 487. So they gave us an initial mass, 0.684 grams of an organic compound. 0.684 grams. So they told us that there was 0.684 grams of some compound. The compound had carbon, oxygen, and carbon, hydrogen, and oxygen, right? We don't know the ratio here. But we know we had 0.684 grams. And now we know how many moles of carbon were in this 0.684 grams, and we know how many moles of hydrogen were in this 0.684 grams. Well, if we convert these back to, or not back, but if we convert it now to grams, knowing that for every 1 mole of hydrogen, there's 1.008 grams of hydrogen. That'll give us grams of hydrogen. And this one up here, same thing, we'll get grams of carbon by saying that there's 1 mole, every 1 mole of carbon is 12 grams of carbon. So we have this number down here, we multiply it by 1.008, so that's 0.09016 grams of hydrogen. So here's our moles of hydrogen that we got from this part. And now we converted that to grams of hydrogen. Here's our moles of carbon, and 0.0282 divided by, or times 12.3384, 0.3384. Now that's our grams of carbon. Now why did we want to go to grams of carbon and grams of hydrogen if what we're looking for is the molar ratio? Well, these values will help us with the molar ratio down here, but we don't have a way to get the molar ratio of oxygen without initially determining how many grams of oxygen there were in the sample. We determine how many moles of moles of carbon there were and moles of hydrogen there were. So we convert that to grams of carbon and hydrogen. Then we subtract that from our initial sample size. So we have 0.684 minus 0.3384. And then we also subtract the 0.09016. All right, so we have 0.684 minus, and we also subtract the grams of, so we subtract from our initial mass the grams of carbon and the grams of hydrogen, and the grams of oxygen ends up being 0.2554. 0.25544 grams of oxygen. All right? So now we have 0.25544 grams of oxygen, and we can convert that to moles of oxygen with 16 grams of oxygen being 1 mole of oxygen. All right, so 0.25544 divided by 16, and it tells us that we had 0.01596 moles of oxygen. All right, so now we have all three. Moles of carbon, moles of hydrogen, moles of oxygen. Carbon is 0.029, whoops, try that again. 0.02982 moles of hydrogen, 0.08944 moles of oxygen, 0.015965. So moles of oxygen is the smallest one. So we divide them all by that. That's going to give us 1 oxygen. 0.08944 divided by 0.015965. That's going to give us H, a value of 5.6. Take carbon there, 0.02982. We divide that by the moles of oxygen, because the moles of oxygen was the smallest one, 5965, and we want to get a whole number ratio, so that gives us carbon 1.867. Those aren't very good values. Let's see if we multiply that by 3. Let's see, make sure we didn't make a mistake. 487. 6.84 grams of an organic compound containing only carbon, hydrogen, and oxygen was burned. 1.312 grams. Let's try this again. 1.312 divided by 44. And that's right there. 0.805 divided by 18. That's how many moles of water there were. Times 2, that's how many moles of hydrogen there were. All right, divide that by, again, well, let's try this one first here. 0.2544. So let's take our hydrogen here times 1.008, and we get 0.9016. That's good. 0.2982 times 12. Oh, sorry, it's 0.02982 times 12, and it's 0.35. Oh, here's a problem. 0.35784. 0.35784. Oh, so this is the problem here. 0.35784. 0.35784. 0.35784. All right, so 0.35784 I wrote that down wrong there. 0.35784. So that makes this grams of oxygen different. That makes this moles of oxygen different. And then we're going to divide them all by a different value here. So we have 0.684 minus 0.35784 minus 0.09016. So that's 0.236 divided by 16. That's how many grams of oxygen there were. And this makes this 0.01475. All right, if we divide that by 0.01475, then that's again going to give us one oxygen, 0.08944 divided by 0.0147. Wait, 0.08944 divided by 0.01475. There. So that gives us 6.06 hydrogens. Carbon 0.0292 divided by 0.01475, and that gave us 2.02 carbons. 2.02 carbons. So C2H6O1. So that's our empirical formula for that compound. Now, we got some weird numbers down here initially, and we knew that, hey, that's not a good whole number ratio, and it's not working out very well. We're not going to be able to find a good whole number ratio. So we double-checked our work. We found out that I had written down the wrong grams of carbon here. As soon as we identified the correct grams of carbon, we could correct that here and determine the correct mass of oxygen that there was, 0.0236 grams. Converted that to moles, and then we could use find the simplest whole number ratio by dividing all of these number of moles by the smallest number. Right? So we got it, 487. All right, 489. When 6.853 milligrams of a sex hormone was burned in combustion analysis, we got 19.73 milligrams of carbon dioxide. Um, 19.73 milligrams of carbon dioxide. This is 489. 19.73 milligrams of carbon dioxide, 6.391 milligrams of water, 6.853 milligrams of the hormone, 6.853. So the total volume, total mass, 6.853. All right, you notice, again, the masses of these are larger than the total mass, and that's because this took the hydrogen and added oxygen in the combustion reaction. This took the carbon and added oxygen into that combustion reaction as well. What is the empirical formula of the compound? Okay. So, we're going to determine, we don't know that it's just carbon and hydrogen. Right? Does it say anything like that? It doesn't say anything like that. Now, and these are in milligrams. All right. So, here we are on 489. And as we left off, we were saying that these three values, our initial value, our total mass, and the amount of water we had, and the amount of carbon dioxide that we had, those were in milligrams. But we just are going to convert them to grams because it'll be the same ratio and it'll remove an extra step that we have to put in here to convert milligrams to grams. All right, so we work with grams. start with this many grams of carbon dioxide, and we determine how many moles of carbon dioxide that is, okay? So we want to keep that number, moles of carbon dioxide. We also want to ultimately determine the grams of carbon, because we need to find the grams of carbon, and same thing with hydrogen, grams of carbon and hydrogen, because we don't know for sure that 6.853 grams is all the mass of this, or all of that mass is due to carbon and hydrogen. It could be that some of that mass is due to oxygen as well. So we did this one, 19.73 grams of carbon dioxide divided by 44, and that's how many moles. We times it by 12, and that tells us how many grams of carbon are in this sample. 6.391 grams of water, that's divide that by 18 grams of water to convert to moles of water, times by 2 to get moles of hydrogen per mole of water. And that'll tell us how many moles of hydrogen. We got 0.710. We multiplied that by 1.08 grams for every mole of hydrogen, and we got that much hydrogen. Now, we take our 6.853, that's the mass of our initial sample that they told us in the book. We subtract our 5.38, and that means there's 1.473 grams worth of mass left. We subtract the 0.71579 from that, and that means we have 0.75721. So 0.75721 grams of mass left after the carbon and hydrogen has been subtracted. So therefore, they don't tell us, but we'll just assume that it's oxygen because we don't know what else it could be. All right, so if we take that 0.75721 grams of oxygen, and for every 16 grams of oxygen, we know that there's 1 mole of oxygen. This will tell us how many moles of oxygen there are, okay? So we have that many grams, we divide it by 16, and we get 0.04733 moles of oxygen. So now we have this many moles of carbon, this many moles of hydrogen, this many moles of oxygen, right? So I'll make a little initial empirical formula here. Well, okay, kind of out of space here, but we have CHO, and it's 0.4484 moles of carbon, hydrogen 0.710, oxygen 0.04733. 0.04733. Divide all of these by the smallest, which is 0.04733, and that'll tell us 1 oxygen. 0.710 divided by 0.04733, and that says that there's 15 hydrogen. 0.4484 divided by 0.04733, and that tells us there's 9.5 carbon, or 9.47 carbons. So now we have a formula of C9.47H15O1. Looks like we have to multiply that by 2 to get C18H30O2. Because 9.47 isn't a whole number. Oh, sorry, not C18, C19. H30O2. So let's see if that's it. 489 C19 H30O2. That's it. Okay, so now we're on to 491. The following are empirical formulas and the masses per mole for the 3 compounds. What are their molecular formulas? Well, we talked about empirical formulas. Empirical formulas are, again, the simplest whole number ratio, but the molecular formula isn't necessarily always the simplest whole number ratio, right? And that example that we have is hydrogen peroxide. The simplest whole number ratio is 1 hydrogen to 1 oxygen, but hydrogen peroxide is the actual molecular formula, okay? So this is the empirical formula, and this is the molecular formula, right? So molecular formula is the correct one, or I mean not the correct one, but the actual how the molecule is, right? So Na2O3. That's an empirical formula, and the mass is 270.4 grams per mole. 270.4 grams per mole. All right, so we're going to try to determine what the actual empirical, or the molecular formula. This is the empirical formula. This is the molecular mass, or the molar mass, and we want to find the molecular formula. Well, we can add this mass up. We know that there is a relationship between the empirical formula and the molecular formula, right? The empirical formula and the molecular formula. That this is, empirical formula and the molecular formula are the same thing, with the difference being that there's some multiplier in the molecular formula in which we have to multiply all these subscripts 1, 2, and 3 by to get the molecular formula. So we can just add up this mass here and find out if it's the molecular mass. So sodium 23 plus 2 sulfurs, 23 plus 35 plus 35 plus 3 oxygens, 48. So this is 141. So if we multiply that by 2, we get 282. Did I miss anything there? Sulfur is what? Oh, 32. Sorry, I made it 35. So it's 32 plus 32 plus 48 plus 23. 135. 135, and this is the empirical mass. Empirical mass is 135. So I can see that the molecular mass divided by the empirical mass is going to give me a value of 2. Therefore, the empirical, or the molecular formula is this, the empirical formula times 2. Does that make sense? Second one, C3H2Cl. C3H2Cl. 12 times 3 plus 2 plus chlorine is 35. Double check, 35.45. So I'm getting 73.45 about. And it says the molecular mass is 147. So 147 divided by that value, and that's again 2. So this is C6H4Cl2. Because the molecular mass, which was 147, this is the molecular mass, and the empirical mass was half as much. So the new molecular formula has to be twice as much, right? All right, C, we have C2HCl. 24, 25 plus 35. So we have 60 about, and the empirical mass is 181. So that's going to be 3. The multiplier between the empirical formula and the molecular formula times 3 to get to the molecular formula. So C6H3Cl3. Okay, so that is 490. Whoops, that was 491. Okay, 493. Compound described in problem 489 was found to have a molecular mass of 290. What's its molecular formula? So this is 493, and it's referring to the one in 489. Its molecular mass was 290. 489, I can't remember what that formula was. It was like C19. H30O2. Was that one? So we have 12 times 9, or no, times 19, plus 30 plus 32. So it has a empirical, this is the empirical formula, And the empirical mass is 290. I just added these all together. 12 times 19 plus 1 times 30 plus 16 times 2, right? So the mass is 290. So the empirical mass, empirical formula, and the molecular mass are the same. So therefore the empirical formula is the same as the molecular formula. Okay? So that's 493. 495. A sample of a compound of mercury and bromine with a mass of 0.389 grams was found to contain 0.11 grams of bromine. Its molar mass was found to be 561. What are its empirical and molecular formulas? 0.389 grams of the sample. 0.111 grams of bromine. .389 minus 0.111. That's 0.278 grams of, what was the other thing? Mercury, Hg. All right. So its molar mass was 561 grams per mole. Okay, so here we go. If we have 0.111 grams of bromine, we can determine how many moles of bromine by knowing that every 1 mole of bromine weighs 81 grams. That's bromine, right? Double check there. Oh, sorry, not 81, 79.9, so it's 80. 79.9 is what I use. And the moles of bromine will therefore be 0.111 divided by 80. 0.001388 moles of bromine. Moles of, what's next? Hg, 0.278 grams of mercury. For every, how many grams of mercury are in 1 mole of mercury? Mercury is 205.9. 200.59, sorry, 200.59. So we have 0.278 divided by 200.59. 0.001386 moles of mercury. So it looks like it's going to be a 1-to-1 ratio, right? 1-to-1 ratio. So it's HGBR, that's the empirical formula, and that mass is going to be 280, right? Because there's 200 for each mercury and 80 for each bromine. So 561 divided by 280 is 2. So the chemical formula, or the empirical formula, is HGBR. Hg2Br2 is the molecular formula. 495, 497 is next. A sample of a compound of carbon, hydrogen, nitrogen, oxygen with a mass of 0.6216. Carbon, hydrogen, nitrogen, oxygen. X, Y, Z. Okay, so we don't know what the ratio is, but we know it has carbon, hydrogen, nitrogen, and oxygen. With a mass of 0.6216 grams, we had 0.1735 grams of carbon. This is how many grams of the sample. 0.1735 grams of carbon, 0.01455 grams of hydrogen. .2024 grams of nitrogen. Its formula mass is 129. Put that down here. 129. Calculate its empirical and molecular formula. All right, so you notice that they didn't tell us how much oxygen, so we have to find that out at some point. Okay, so we have to go to moles of carbon. Oh, we can find that out now, because we have grams of sample minus all of these, and whatever is left is going to be grams of oxygen, right? So 0.6216 minus 0.1735 minus 0.01455 minus 0.2024, so there's 0.23115 grams of oxygen. Formula mass is 129. All right, so we can know that there's 12 grams of carbon for every 1 mole of carbon. This will tell us how many moles of carbon there are. 16 grams of oxygen, 1 mole of oxygen, 14 grams of nitrogen, 1 mole of nitrogen, 1.008 grams of hydrogen, 1 mole of hydrogen. So 0.1735 grams of carbon divided by 12 will give us 0.01446 moles of carbon. 0.01455 divided by 1.008, 0.014434 moles of hydrogen. 0.2024 divided by 14, 0.014457 moles of nitrogen. 0.23115 divided by 16, 0.014468 moles of oxygen. So we can see that they're all in a 1-to-1 ratio because they all have this many moles, right? So we can see that the formula is, the empirical formula is CHNO. Now, if we just add that up together, that's 12, 13, plus 14, 17, plus 16, 17 plus 16, 33, right? 33. So 129 divided by 33 equals 3.9. Is that right? Let's try to do that again. 12 plus 1 plus 14 plus 16. Oh, 43. Sorry, 43. 43. So 129 divided by 43, and that's 3. So this is the empirical formula. And the molecular formula equals C3, H3, and 3O3. $4.99. The balanced chemical equation contains the term BaOH2 8H2O. How many atoms of each element does this represent in the molecular view? How many moles of each element does this represent in the laboratory scale? Oh, I think, so what they're trying to say is 2 BaOH 8H2O. So this is barium hydroxide, octahydride, right? And we have 2 of these. So this means we have 2 of these, 2 moles of barium hydroxide, 16 moles of water, right? How many atoms of each? Well, barium, 2 of these. Oxygen, well, there's 2 oxygens in this little unit. There's 8 here. That's 10, so we have 2 of those all together, so that's 20 oxygen. Hydrogen, there's 2 here, and 16 here, 16, 17, 18, 18, and 18 are 36. So we have 36 hydrogens, right? So 2 bariums, 20 oxygens, 36 hydrogens, right? And how many barium hydroxides? 2. How many water molecules? 16. How many moles of barium hydroxide? 2 moles of barium hydroxide, 16 moles of water, 2 moles of barium hydroxide octahydrate. 499, 4101. A balanced chemical equation contains the term 411. Write the equation that expresses in acceptable chemical shorthand the following statement. Iron can be made to react with molecular oxygen to give iron 3 oxygen. Oxide. Iron can react with molecular oxygen to give iron 3 oxide. Right? Write the equation that expresses in acceptable chemical shorthand the following statement. Iron can be made to react with oxygen to give iron 3 oxide. So we just have to balance this equation now. We have 3 oxygen over here. If we put this 3 and make that 2, then now we have 6 here and 6 here, and we have 4 there, so we have 4. Is that right? 4 iron, 3O2, 6. Let's just double check that one to make sure we're not missing something. 4101, 4 irons, 3 oxygens, and 2 Fe2O3s. So they included the phases here, which is a good idea. Okay. Good. 4103. Balance the following equations. Calcium hydroxide reacts with hydrogen chloride to form calcium chloride in water. Calcium hydroxide. Hydroxide is -1 and calcium is +2, so we need 2. Plus hydrogen chloride reacts together to form calcium chloride and water. Is that right? Yeah. All right, so we see that we're going to need 2 of these because we have 2 chlorides over here. 1 calcium, 2 chlorides, 2 chlorides. And we're going to get 2 molecules of water. There's 2 hydrogens here, 2 more hydrogens here, so that's 4 on the left, 4 on the right. 2 oxygens on the left, 2 oxygens on the right. So that's the balanced equation there. Silver nitrate, Ag, silver nitrate, NO3. Silver just forms +1 ion, that's all. Nitrate has a -1 ion, so silver nitrate. All right, silver nitrate and calcium chloride react to form calcium nitrate and calcium chloride, CaCl2. React to form, oh, I don't need parentheses there, this is